So get this. What if I told you that some of the fastest systems on the entire internet, we're talking Google, social media, all the big stuff, they actually rely on being, well, wrong sometimes. It sounds kind of nuts, right? But that's the secret sauce behind one of the most clever, simple, and honestly powerful data structures out there, the Bloom filter. It's this amazing tool that basically embraces probability to make our digital world just incredibly efficient. So yeah, let's dive in and see how the power of probably makes pretty much everything faster.
All right, here's the game plan. We're going to start with a really expensive billion-dollar kind of question. Then meet our hero, the probabilistic bouncer. We'll break down exactly how the filter works, uncover the one little catch, the whole false positive thing, and then we'll go looking for these filters out in the wild.
Okay, first up, the billion-dollar question. Let's really set the stage here with a super expensive problem. Imagine you're running a huge service, something massive, with a giant database. Every time a user asks for something, you've got to be fast. But what happens when they ask for something that isn't even there?
And this right here, this quote from a developer on Stack Overflow, it just nails the problem perfectly. They're talking about a nightmare scenario that we call cache penetration. Basically, their system is just getting hammered with requests for data that doesn't exist. It's a total waste of resources, and it's causing a major performance hit.
And this is that vicious cycle in action. It's a real resource hog. So look, a client asks for a key that just doesn't exist, step one. Then the system checks its super fast cache, like Redis, and whiff, it's a miss. So what happens next? It has to go all the way to the main database, which is way slower. The database churns away, does a whole bunch of work, only to come back with, you guessed it, nothing. The entire process just burns time, CPU cycles, and cache, all to say, nope. Now imagine this happening millions of times a minute. Your whole system can just grind to a halt.
So the big question is, how do you stop this bleeding? You can't just block every request. That's not going to work. What you need is a really fast, super lightweight way to screen them, kind of like a bouncer for your database.
And that bouncer, my friends, is the Bloom filter. Let's just quickly break down what this thing is. When we say space efficient, we mean it's tiny, incredibly small, which is absolutely crucial for performance. Probabilistic? Well, that means it's playing the odds. It's not about 100% certainty. And its entire job, its whole reason for being, is to answer one simple question really fast. Is this item maybe in our set? And honestly, the bouncer analogy is perfect. Think about it. Instead of making your database, the fancy VIP room, do a full, expensive background check on every single person at the door, you put this Bloom filter out front. It's a bouncer with a really simple checklist. It can't tell you for sure if someone is on the list, but it can tell you instantly if someone is definitely not on the list. And that saves the main system a ton of work. All right, so let's get into the nitty-gritty. How does this bouncer actually build its list and do these checks so fast? The magic really boils down to two simple things: hashing and bits. Okay, here's how we add an item. Say we want to add the word potato to our list. The key here is we don't actually store the word potato. No way. Instead, we take that word and we run it through a few different hash functions. Think of these like special blenders. Each one spits out a number, and we use those numbers to point to specific spots in a big long line of zeros and ones. That's our bit array. And at each of those spots, we just flip the bit from a 0 to a 1. That's it. So what you're left with is this bit array that started out as all zeros, but now it has a few ones flipped on. That pattern of ones, that's the fingerprint. That's the ghost of the word potato. We've stored the idea that potato is in our set without storing the actual word. And that is what makes this whole thing so ridiculously space efficient. Okay, now for the fun part, checking for an item. Let's say a new word comes along, like cabbage. We do the exact same thing. We run cabbage through the exact same hash functions, and we get a new set of positions. Then we go look at our bit array at those spots. And this is the whole trick. If even one of those spots is still a 0, we know with absolute 100% certainty that cabbage was never added. Game over. It's a definite no. But if all the bits are 1s, well then we can only say it might be in the set. And you probably just caught that all-important word, might. This is the catch. This is where the whole probabilistic thing comes into play. It's not perfect, but weirdly enough, its imperfection is its greatest strength. So what's the catch? Really, for all this amazing speed and space saving, what's the trade-off? Why can we only say it might be there? Well, here's how it can get tricked. Let's say after we added potato, we also added cabbage, which flipped a few more bits to 1. Now our bit array is getting a little more crowded. So what happens if we check for tomato, a word we know for a fact we never, ever added? It's possible, just by pure random chance, that the hash functions for tomato point to spots that were already flipped to 1 by potato and cabbage. So the filter looks, it sees all 1s, and it goes, yep, tomato's probably here. That's a false positive.
And this right here is the absolute key to understanding Bloom filters. It's a one-sided error. It can have false positives, it can lie and say something is there when it isn't, but, and this is the part you really gotta get, it can never, ever have a false negative. If the Bloom filter says an item is not in the set, that answer is 100% gospel truth. It is definitely not there. And think about our original problem with a cache. This is perfect. We don't mind if a few bogus requests slip through by accident. What we care about is blocking the vast, overwhelming majority of them with total certainty.
Okay, so now that we get the genius behind this trade-off, let's go on a hunt. Let's find these filters out in the wild and see the real-world impact they're having. And trust me, they are everywhere. We've already talked about preventing cache penetration. That's a big one. But think about spell checkers in your word processor. They use a Bloom filter to quickly check if a word you typed might be in the dictionary before doing a slower, full search. Databases use them all the time to speed up queries. CDNs, the networks that stream videos and websites to you, use them to figure out which server is closest to you that has the content you want. They're even used in network security to spot known malicious websites or IP addresses. And here are a couple of those big use cases, visualized. On the left, you've got web caches. A single tiny Bloom filter can represent all the content stored across a whole bunch of different servers. So you can do one super fast check instead of asking every single server. And on the right, for databases, a filter can be a huge performance booster for figuring out how two big tables of data overlap. It's just incredibly efficient.
And the best part? It's not a one-size-fits-all solution. It's totally tunable. You get to decide on the trade-off between space and accuracy. You can see it here. If you go with a really small filter and just a few hash functions, hey, you save a ton of space, but your false positive rate is going to be higher. But if you're willing to use a larger bit array and you pick the optimal number of hash functions, you can get that false positive rate down to almost nothing while still being way, way more space efficient than any other option.
But no matter how you tune it, whether it's big or small, a higher rate or a low one, you have to remember the golden rule, the one number that never ever changes. The false negative rate is always 0%. That is the guarantee. If the filter says no, the answer is no, period. And that rock-solid certainty is what makes this probabilistic little tool so reliable and so powerful. So really, the Bloom filter leaves us with this pretty fascinating idea, right? It teaches us a huge lesson that sometimes being probably right is just infinitely better than being perfectly slow. And it really makes you wonder, doesn't it? Where else in all the technology we use every day are we making these kinds of trade-offs? Where are we accepting good enough instead of perfect to make our digital world faster, smarter, and more efficient?